talk is the last time to sign up for the banquet. The second announcement is that those of you who are parking on Cherry Street Garage, that's going to be closed for repairs or something. So you can park on Mountain and Second. No, at the Second Street Garage, Speedway. Speedway Mountain. And we'll get to it. Okay, so at the end of last time, I said a little bit about this theory of Raynaud, which associated to any rigid space X, so say X is a quasi-compact and quasi-separated rigid space, and again, you can just think separated if you don't know what quasi-separated is, rigid space over K. And so given this, there exists these X, which are these, what we'll call these admissible formal R schemes. So these were built by gluing finitely many formal spectra of topologically finitely presented and flat R algebras. So some kind of, not like schemes of finite type, the basic building blocks are sort of these restricted power series rather than polynomials, kind of integral versions of affinoid algebras. And the theorem of Raynaud, well, the first of many of his theorems in this direction, was that there was such an X such that its generic fiber is isomorphic to X, where again this guy was obtained by gluing the rigid spaces associated to the affinoid algebras coming from the basic open affines within this space. And so this is a very powerful tool, as I alluded to briefly at the end of last time. And I just want to make one further comment about this in the direction of pointing out how, associated to an initial rigid space, we can build some much more intricate kinds of topological spaces. Recall I mentioned last time that although the rigid spaces are quite nice for the purposes of building a coherent sheaf theory, and they do certainly provide a more general category of abelian sheaves, for the purposes of having a very workable abelian sheaf theory, they're not really the best point of view because stalks computed at actual points of this space are not quite adequate for the study of general abelian sheaves. And so to that end, let me show you a more interesting kind of topological space that we can cook up out of X in a functorial way. Well, associated to every X, there are these formal models. And in general, there might be many of these. But Raynaud identified that if X and X prime are two formal models, then there exists what's called an admissible, what I refer to as something analogous to blow up in the closed fiber. There's an operation called admissible formal blow up along certain coherent ideal sheaves on these two spaces. This operation does not change the associated rigid space, though it does drastically change the underlying topological space of the formal scheme. And so there is such a guy that dominates both of these. And in fact, once I tell you this and these maps, it recovers this identification in the sense that YK maps isomorphically to both of these, and this recovers this identification. So that said, the point is if you consider the collection of all formal models for X, so the collection of all these X's is naturally an inverse system. It's a filtered inverse system of formal schemes. Any finite collection is dominated by another one via this kind of map, and the map on full schemes is uniquely determined by the identification of rigid spaces, given that it exists compatible with this, and therefore it makes sense in an unambiguous way to form the inverse system of the underlying topological spaces with respect to these maps. So it's well defined to define this in terms of X. Say associated to X, we associate a new topological space called its adic space, which is the inverse limit of the underlying topological spaces of all these X's. Now this is some god-awful beast, but it turns out by work of Hochstar and spectral spaces, this is not such a terrible topological space. And by using Raynaud's results, it's actually functorial in X, even though any particular formal model is not quite functorial in X. And in fact, it turns out that you can convert questions about abelian questions about sheaves on this rigid space with respect to the Tate topology into questions about sheaves on this ordinary topological space. And this actually makes it possible to work with ordinary sheaf theory here to analyze some sheaf theoretic questions there. On the other hand, this kind of topological space is rather complicated and hard to, if you thought those Berkovich P1s were hard to visualize, these are more complicated. So I'm not going to say anything more about these adic spaces. And what we're going to do today and the next time is we're going to study these Berkovich spaces, which also can be associated to a rigid space. They have much more familiar kinds of topological properties. These things are very non-Hausdorff. The Berkovich spaces, as you've seen, can be quite tree-like. Topologically, they're not quite so bad once you get used to them. But you should just keep in mind that there are other points of view on how you can enrich a rigid space to something that, in a sense, has much nicer topological structure. So I won't say anything more about these rigid guys. Let me just, you know what? I guess since we're not in Israel, we'll just leave this guy over here. And from now on, I'll go left to right. OK, so now let's move to Berkovich spaces. Is this? Yeah. OK. So we've seen these come up in several talks. And so my aim today is to discuss a little bit more systematically how the aphanoid theory of these Berkovich spaces works. And maybe at the end, I'll say a little bit about the globalization process, or at least one of the reasons why it's a bit more complicated than the usual formalism. I'm sorry? Oh, a little bit more focus. OK, so I know how to use this machine, so I'm just going to switch to there. Sorry about that. OK, so shalom. OK, so we're going to study just pretty much the aphanoid theory. If there's time left at the end, then I'll discuss why we have to go a bit beyond the framework of locally ringed spaces to discuss the globalization process. So to that end, we need to introduce a generalization of the theory of Tate algebras. It was mentioned before how in the Berkovich theory, one can in some sense consider disks whose radii are arbitrary positive real numbers, not just things in the divisible group generated by the value group. And so let's introduce generalized Tate algebras. So we have generalized Tate algebras. So these will again be Banach algebras. If I fix some positive real numbers, R1 through Rn, I want to consider the coordinate ring of what should be the polydisk in n variables whose coordinates are bounded in absolute value by these numbers. And so I'll define this to be maybe T sub R of k. And I'll denote it k angle brackets R1 inverse x1 up to Rn inverse xn. And what is this? This is going to be the set of formal power series aj, xj in these n variables, with the condition I want to say that it converges on the polydisk whose coordinates are less than or equal to the r's. Now, these r's may not be in the divisible group generated by the value group. Okay? And so the definition is that we take the condition that if I take aj r to the j, meaning aj times, so this I mean aj times r1 to the j1, rn to the jn, that these real numbers tend to 0. Whoops, let's put some absolute values so that multiplication actually makes sense. Okay? So the condition is that these should go to 0, and morally, if these actually did make sense as radii over k, this would in fact be the convergence condition on that polydisk. And let's find a norm on here, the norm of such a power series in this generalized Tate algebra with respect to these r's with a maximum of these numbers. Okay? And it's an exercise in the notes to check that this is in fact a multiplicative norm. So this is a multiplicative norm. Gives this a structure of a K-Banach space. In fact, a K-Banach algebra. But of course, the proof of the multiplicativity requires a little bit more thought because you can't scale to the unit case by copying the proof of Gauss's lemma. Now, these rings, it's not actually a priori evident that these are Noetherian. Well, I guess it wasn't obvious for the Tate algebras either, But these are a little bit more subtle to work with, and let me just show you one example to demonstrate the subtle nature of these rings. So let's consider the following example. So suppose I do give you a positive real number that's not in the divisible group generated by the value group, and let's consider what I'll call k r inverse x and r x inverse, by which I mean you take the two-variable ring where one variable is bounded above by r in absolute value, the other variable is bounded above by r inverse in absolute value, and then you actually set them equal to each other. Sorry, thank you. Okay? So morally, you want to think about this as corresponding to the condition absolute value x equals r. Something like circle of radius r, but this r is not in the value group. And it's a very curious fact, which is outlined in an exercise. This thing is actually a field. Okay? And if you take this norm, r1 over r, this is in fact an absolute value on this field, which makes x have absolute value r. No surprise there. So this, you would like to think this should be a one-dimensional ring. And in fact, if you make a sufficiently large extension on the coefficient field to put r in the value group, like base change this by itself, then in fact it does become a one-dimensional ordinary aphanoid algebra. So in fact over here, maybe I'll just say that, well, we'll come back to the special kinds of r's in a moment. But you should just appreciate that these things, if we're going to try to study dimension theory or contemplate a dimension theory for spaces associated to these rings, we're not going to be able to use commutative algebra dimension theory, because morally, the space associated to this ring should be one-dimensional, but in terms of algebra, it's indeed quite far from one-dimensional. Okay, so that said, maybe I'll mention as another example, if k over k is an extension field with the r's in the value group, and you see this construction provides a non-Archimedean extension of k, namely this guy, such that there's an element, namely x, whose absolute value is r. So if I give you some positive real numbers that maybe are not in this divisible group, you can always find an auxiliary field extension and iterate this construction to actually put these r's in the value group. So given any r's, you can in fact always find such a field. And then if you take the tensor product of the Tate algebra over k against this big K, this is in fact a sort of old-fashioned or isomorphic to an old-fashioned Tate algebra over capital K. Because over capital K, we can scale the variables dividing out by elements whose absolute values are the r's to move them to things that have absolute value 1 on the nose. Okay? So you can convert it to an ordinary Tate algebra after a massive extension of the base field. Okay, so having introduced these generalized Tate algebras, let's now define a generalized notion of aphanoid algebra. And so this is where I run the risk of a little bit of confusion. We're now going to change one of our earlier definitions and actually define k-aphanoid algebra all over again. So a k-aphanoid algebra, in our new sense, not to be confused with the old sense, which hopefully won't be possible because we're going to stay in this new setting for the next 2 talks. Can't make any promises about the other talks. So this is a k-algebra A, a k-Banach algebra A, such that there is a continuous surjection from one of these generalized Tate algebras onto A with, well, continuous, so the kernel is a closed ideal, and so the quotient is in fact a Banach space, meaning you do get a residue norm on this, and I'll just say with the residue norm equivalent to the given norm on A. So one subtlety in this business is ordinary aphanoid algebra, as I mentioned before, that the Banach algebra structure, any two such are equivalent to each other, so you don't have to keep track of whether norms are equivalent. In this new setting, in some situations, you do have to be very careful about this, so we have to add in this extra condition. If these r's were all 1, this last condition would in fact be automatically satisfied, so you wouldn't notice it, as would this continuity condition as well. Anyway, so that's the definition of an aphanoid algebra. And if there might be a zillion such presentations, if you can choose all the Ri's to be 1, which is the old-fashioned case, we'll just call a strict k-aphenoid algebra. And of course, one of the wonderful things in Berkovich's theory is the fact that you can deal with these non-strict things, and this is exactly why we will be able to contemplate disks of arbitrary real radius. And as you've seen in some of the earlier talks, the ability to have an arbitrary real radius is crucial. That's the radius is the parameter of these paths. Yes? Okay, so now comes another important point. So in Berkovich's theory, it is in fact also possible, so we allow the possibility that the absolute value of k may be trivial. Now, if the absolute value is trivial, so this is discussed in the notes. Let's just say for the purposes of the talk, to keep things simple, I will ignore that possibility, though I should point out that this does actually have, Berkovich has found some interesting applications of this case. So it's kind of an interesting feature of the theory that you can allow this possibility, but it complicates some statements, so I'll ignore it for the purposes of the talk. It is discussed in the notes. Okay, so these are the basic building blocks of the theory. And now let me talk a little bit about the topological spaces that we want to associate to these algebras. For example, the space associated to this should be something like a polydisk with polyradius given by these various R's. Okay, so now let's discuss the associated topological spaces. So these were brought up in Baker's talk. So the spectrum of A. So let me take A just to be, well, let's do as kind of Matt did, so this will be a little bit of a review, just an arbitrary commutative Banach ring. All right, so really it should be A, comma, norm. All right, and so let me recall what the so to motivate this definition, let's first discuss some motivation. Yes? Okay, so let me tell you, thank you. So let me tell you a couple of interesting commutative algebra properties of these rings. All right, let's put this over here. I'll just say the TR of K has familiar properties, so that's what I'll write. And what I mean by that is it turns out that these are, in fact, Noetherian rings in which all ideals are closed, and they have other properties similar to the old Tate algebras. Of course, the dimension theory is a bit complicated, as we've seen in some contexts. And in fact, you should keep in mind that the way you prove things about these rings at the beginning of the theory is not so much by redoing the old proofs in this generality, but rather you prove results that it suffices to prove various things after massive extension of the base field. Then you increase the base field to put the R's in the value group, and then you pull down results from the classical case. So many of the familiar properties, particularly Noetherian and closed ideals, do in fact remain true. Okay. So now coming back to this Banach ring situation, just to motivate the kinds of spaces that we're going to want to consider, let me address a very basic kind of question that already illustrates some of the technical shortcomings of the classical theory, which is, let's suppose that A is a QP aphenoid algebra, and let's consider the ring map A goes to A sub CP, by which I mean the corresponding CP aphenoid algebra. And the problem is that there's no map. This is a perfectly nice continuous map of Banach algebras. Of course, over QP, this guy is absolutely enormous. But there's no natural map on max spec backwards. And in general, the problem is, if I do give you a CP point, X, right? If you contract this back to here, then the kernel of this map, let me call this absolute value sub X. This is a multiplicative, continuous, bounded, multiplicative semi-norm on A, and the kernel, as with any semi-norm, call that P sub X, this is a prime ideal of A, but is usually not maximal. Okay? On the other hand, if you look at A mod P sub X, this is a domain on which this thing gives an absolute value. And therefore, it passes to the fraction field. So a point over CP does induce an absolute value on the algebraic residue field at the point P sub X in spec A. but it's not a finite extension of K. This is usually not K finite. So what have we actually accomplished in this way? Given a point over here, we haven't gotten a point in max spec, and in particular, there's no canonical absolute value on the fraction field of this domain because it's not finite over K. On the other hand, we have obtained a preferred absolute value by using this point x. And so what we do get out of this, so let me call it h of x to be the fraction field of a mod px, and then you take the completion with respect to this absolute value. And so we have this map A to hx. This is a non-Archimedean field. It's, of course, usually quite large over K, and A generates a dense subfield, generating in the sense of taking ratios of elements in the image, okay? Namely this subfield of which this is the completion. So what we see is, associated to this point here, we haven't gotten a point of this, but we have gotten a kind of non-Archimedean field-valued point of A. And so this is very reminiscent of the difference between classical and modern algebraic geometry over a field, where the points of the scheme correspond to, in some sense, arbitrary field-valued points of the coordinate ring, roughly speaking, rather than just points valued in finite extensions. And so you might think, hey, maybe we should try to cook up a space which isn't just points of A valued in finite extensions, that's essentially what this is, but why don't we look at points of A valued continuously in arbitrary non-Archimedean extensions? Said that way, it makes one wonder why it took so many years for people to think about this, come up with this approach. In any event, now we're going to exactly follow this strategy, which is very reminiscent of scheme theory, but fields are replaced by non-Archimedean fields. So now let me make the definition. So the spectrum of A is, so script M of A, and this is the set of all, well, as Baker defined it, bounded multiplicative semi-norms on our Banach algebra. Okay? And as this construction sort of suggests and is sort of fleshed out in one of the exercises, given a bounded multiplicative semi-norm on here, you get an absolute value on the ring modulo the closed kernel of the semi-norm map. That's a domain. And therefore, you get an absolute value on the fraction field, and you can complete it, and that will give rise to a map from this ring into a non-Archimedean field such that this guy has dense image, and the absolute value on this field composed back to here recovers your bounded multiplicative semi-norm. So roughly speaking, this is the set of all non-Archimedean field-valued points, non-Archimedean field-valued points of this data. Okay? And so it's very reminiscent of the idea of taking a spectrum, somehow encoding the non-Archimedean structure. Okay. So this is the definition of the spectrum as a set. And now let me briefly recall what the topology is on this set. I'll describe it in a way slightly similar to what Matt did. But let's first actually look at an example where there's no topology because there's almost no set. Suppose this is a general definition for any Banach ring at all. Suppose you take A to be K, a non-Archimedean field. All right? And let's say with absolute value denoted this way. Notice this definition refers to the ring and the norm. Very important point. This depends on the norm only up to equivalence. Meaning, if I replace the norm with an equivalent Banach algebra norm, the concept of boundedness does not change. So in particular, if I use an affinoid algebra, which has no canonical norm, but they're all equivalent to each other, this set is unambiguous just for any affinoid algebra without having to specify this data. In general, you do have to specify this data. So for example, and there's no, this doesn't refer to any underlying field. This may not contain a field like Z. So A is a non-Archimedean field, and now the point is, if I give you this guy, if this is a bounded multiplicative semi-norm, well, this doesn't have very many ideals. So i.e., if this is an absolute value, such that, because this is a field, such that this guy is less than or equal to a constant times this guy, that's the boundedness condition, you play the same old game where you evaluate on nth powers then you pull out the n, and then you pass to nth roots, and then you get this for all n, and therefore this guy must be less than or equal to that guy for all x. But you apply this to x inverse, assuming x is non-zero, and then you get the reverse inequality. So you conclude that these are in fact equal for all non-zero x, and of course also for x equals 0. So the upshot is, in this case, m of k equipped with this absolute value is just the one-point set consisting of the absolute value. Okay? So for a field, it's automatically forced that if it contains a non-Archimedean field compatible with this, it's automatic that this semi-norm restricted to the field actually coincides with that given absolute value. Okay? So this is kind of an amusing example, not very interesting one because it's just a one-point set. But in any event, now we can record a couple of basic facts about these spaces once we define the topology. So I'll just say that the topology is defined by base of opens around a point. So if I give you a particular bounded multiplicative semi-norm, a base of opens around it is given by you pick finitely many elements in the ring, you pick finitely many positive real numbers, and you consider all those norms bounded multiplicative semi-norms with the property that if you evaluate it on one element and you see how far that is from the initial point evaluated on that element, that they're within epsilon j of each other for all j. Okay? So this is a base of opens around, and these guys here are elements of A. All right, and these are positive numbers. So this is a simple base of opens. So the topology is actually quite reasonable. And the fundamental facts are that M of A with this topology is compact Hausdorff. And it's non-empty if and only if A is not 0. And also, this is, let me just say, as a topological space, this is functorial in A. All right, so if I give you a bounded linear map, a bounded map between k-Banach algebras, then in fact you do get the induced pullback map on absolute values is in fact continuous with respect to this Berkovich topology. And so a very interesting example of this functoriality is, suppose I give you A as a k-affinoid algebra in the generalized sense that we've been discussing, and k over k is a non-Archimedean extension field. Then if you take the completed tensor product, this is now a capital K affinoid algebra in the generalized sense we've been discussing, and this gives a map from A to AK, from a little k affinoid to a capital K affinoid, and thereby gives rise to a pullback map backwards on these spectra. And this is in fact a continuous surjection. So the ability to map a space over one field to a space over a smaller field is totally familiar from scheme theory. You have an algebraic variety over Q. The complex fiber maps back to the variety over Q. Most of the complex points which have transcendental coordinates will map onto the generic point of the guy over Q. That operation doesn't make sense in classical algebraic geometry where you only have points valued in Q bar and C. And similarly here, we now can map the space over the big field to the space over the small field. From the classical point of view, the transcendental points will get mapped onto some of the non-classical points in this spectrum. Okay? So we've recovered, now we've gotten around the problem that a rigid space over CP has no meaningful map to a rigid space over QP. In this context of these topological spaces, change with the base field is a much more straightforward operation. On the other hand, it comes at the expense of some cost in terms of the ability to visualize what's happening in these spaces. So that said, let me actually discuss one other example of this functoriality. So let me, fibers. So say I give you A to A prime is a map of k-affinoid algebras. So you get a pullback map on these absolute values. So again, if this map is phi, this is just the map that takes a point, which is an absolute value, to its composite back to here. So even if this was a norm, this may well have a kernel, right? So semi-norms go to semi-norms. Norms may not go to norms, but the boundedness is fine because this is continuous. In any event, we have this natural map. Suppose I give you a point x in here. Well, if I give you x, you get out of this, there's a canonically associated non-Archimedean field, which is you take the ring modulo the kernel of the semi-norm. This is a domain. Take the fraction field and take the completion with respect to the absolute value induced by the semi-norm. You've killed off the kernel. Now you have a multiplicative norm on the domain, becomes an absolute value on the fraction field. Take the completion. So given any point, we've associated a non-Archimedean field. If this was an affinoid algebra and this was a classical point, this would be the old-fashioned residue field. On the other hand, if this was an affinoid algebra and this is some new point, like type 3, this would be a much bigger field. Anyway, what's the fiber over this? Well, to this space, there's a natural map from A completed tensor product over A with h of x. This guy here is hx affinoid. Don't ask me why it's denoted h. Well, you can ask, but I don't know the answer. So this is an hx affinoid algebra. There's a natural map to here induced by the pullback for the natural ring map. And it turns out that this is, in fact, topologically, this goes homeomorphically onto the fiber over this point. So you can discuss fibers of maps much as you do in the context of schemes. And the fiber corresponds to an affinoid algebra over the natural non-Archimedean field associated to the point. So the basic relation between the commutative algebra and the topology works out quite nicely. But you do have to keep in mind, even if K is algebraically closed, as we've seen in Matt's talks, that M of A for K affinoid A nearly always has lots of non-classical points. Okay? And in fact, let me just make a remark in this direction. Suppose I give you A is a strict K affinoid algebra, so a sort of a classical K affinoid algebra, then there is a natural map from the classical rigid space to this Berkovich spectrum, which associates to every classical point the bounded multiplicative semi-norm, which is absolute value of f of x. Okay? That has a massive kernel, which is the maximal ideal at x. Nonetheless, there's a natural map from this set to this set, and in this setting, this in fact has dense image and induces the canonical topology. Okay? And the picture that you should have in mind here is of the rational unit interval inside the real unit interval. If I give you the real unit interval and you look at the rationals inside with the subspace topology, it's a totally disconnected space, but it's dense inside the real unit interval, which is a nice compact Hausdorff space. And that's, in some sense, kind of like this situation here. So it's sort of as if the fact that Tate was able to create this theory which kind of forced compactness on these would be sort of as if you didn't know what the real numbers were, you only knew the rationals, but you still kind of try to define the topology on the rationals that somehow encoded the compactness of its completion without knowing what the real numbers are. So you could think about trying to do that. Anyway, so maybe it makes you appreciate more how remarkable it is that one could develop the theory for these without actually having these spaces available. Okay, and so having mentioned this fact, let me remind you another property that was mentioned in Baker's talk, which had to do with the nice topology on these spaces. And so the key property there has to do with connectedness. So I've told you that these are compact Hausdorff, and it's a nice theorem that, again, if I give you A is K affinoid in our generalized sense, then M of A is connected if and only if it's path connected, and that's if and only if the ring has no non-trivial idempotence. So, for example, if you take a standard Tate algebra, then you do get a connected space. But keep in mind, this connectedness is a very delicate operation. If you take A to be the Tate algebra in one variable, and then let's consider the associated Berkovich spectrum associated to this. So this is a connected space, and inside of here is this special point corresponding to the Gauss norm. If you actually take out the Gauss norm, then in fact this space breaks apart into lots and lots of pieces. So this thing is actually quite disconnected. And roughly speaking, the connected components, this is discussed in one of the exercises in the notes. The connected components of this space actually correspond bijectively to closed points of the affine line over the residue field of K. So again, here K is a non-trivial absolute value. So globally, the spaces, the topology does have some nice relation to the ring theory, but once you start pulling out some non-classical points, it can be very complicated to describe. Well, it can be surprising if you have no prior experience with these, sort of what might happen. And keep in mind, in particular, unlike in classical algebraic geometry, you have an algebraic scheme over a field. Sorry, you have an algebraic variety over a field with just closed points, and you look at the associated scheme, the topology doesn't change. You can detect equality and inclusion of Zariski open sets in the classical setting by going to the scheme and vice versa. Okay? The sheaf theory, everything is the same. On the other hand, here, you remove this non-classical point. Well, actually, this can be interpreted in the classical theory, but it doesn't correspond to removing any point from the associated rigid space. Okay? So the relationship between properties of the rigid space and properties of the associated Berkovich space, with this coming from the coordinate ring, is a slightly delicate thing to get used to. That said, I've just defined the topology. Although it's a compact Hausdorff space, we're not going to want to study, well, we are going to want to work with the topology of this space, but the topology, the open sets, don't necessarily know anything about the analytic structure in the ring. So we want to define a class of interesting subsets that will correspond to the rational Laurent-Weierstrass domains, perhaps affinoid subdomains of the classical theory. And here we run into one of the fundamental ways in which this theory really takes some getting used to, which is that if the affinoids are supposed to correspond to compact Hausdorff spaces, then we have to expect that the rational domains, the Laurent domains, and the Weierstrass domains in this space, there should be compact Hausdorff subspaces. So they're not going to be open sets. And so when we're going to try to globalize these things, we're going to try to glue affinoids along subdomains, we're going to need to glue along closed sets. And so if you're used to thinking about locally ring spaces, this is a little bit disconcerting at first. But as with all ideas, with enough experience, it becomes to seem quite natural. So now let's contemplate how to define rational, Laurent, and Weierstrass domains. And again, the surprise, so to speak, is these are not going to be open sets. So let's fix A as a K-affinoid algebra, again in this generalized Tate sense. Although you can, by the way, if you prefer only to think about the classical affinoid algebras, I mean, that's fine too. These non-strict ones with the funny real radii are quite nice to have around, but already the classical ones give rise to these, very exotic topological spaces. So we have our K-affinoid algebra, and let's first do the Laurent case. So let's choose a bunch of elements, A1, AN, A1 prime, AM prime, in here. And now what we want to do, so now here's the interesting wrinkle. Remember, when we defined a Laurent domain, we imposed the condition, we looked at the points where the absolute values of these, which is to say their absolute values in the completed residue fields at these points, were bounded above by 1, and these are bounded below by 1. And I mentioned that you could have allowed yourself to replace the number 1 with other real numbers in the divisible group generated by the value group, but they gave no extra generality. Well, here we can do even better. We can impose inequalities with arbitrary positive real numbers. So let's consider the set of points in M of A with the property that the absolute AIX, so let's also choose R1, Rn, S1, Sm greater than 0. Consider these conditions. The A's are less than the R's, and the A primes are bigger than or equal to the S's, where again, let me remind you, by absolute AX, what I mean is the absolute value of the image of A in H of X. And I use the absolute value arising from X. So let's consider this locus, but these are arbitrary positive real numbers. Okay? And this is, in fact, associated to this, we want to consider, well, kind of a generalized Tate algebra, R1 inverse T1, Rn inverse Tn, S1 U1, Sm Um, and then mod out by the relation Ti minus Ai and then aj prime uj minus 1. Okay? So associated to this domain, we want to contemplate what should be the corresponding coordinate ring. This is exactly the analog of a rational coordinate ring domain, except we're using this kind of generalized Tate construction with real numbers corresponding to these conditions, and then we impose the usual relations as in the classical case. And let me just say that this guy, this has the expected universal property for maps from A to B, let's just say for simplicity, let's just say any k-Banach algebra, if you call this set U, such that M of B lands inside U. Meaning if I map this to any k-Banach algebra such that the induced map on spectra lands in U, then this map uniquely factors through the structure map to here. Okay, so you have a universal property using the universal property of Tate algebras, the generalized Tate algebras, with these funny real coefficients, but those universal properties, the proofs, carry over almost exactly as in the classical case. So that's the general definition. A Laurent domain is a subset of this type, and maps to it, induced by k-algebra maps, k-Banach algebra maps, are in fact characterized by this set theoretic condition exactly as in the classical case. And I'll leave it to your imagination to guess how you would define rational domains. It's exactly the same condition. I give you an n-tuple of elements and another element which simultaneously have no common zero on the space. And you impose some inequalities, much like in the rational case. And once again, we have the extra technical advantage that we can put arbitrary, real positive scaling factors in the defining inequalities and not just have to use just the scaling factor of 1 or things in the divisible group or the value group as we did in the classical case. So let me just point out, key comment, that in this situation, the induced map from, let me just say, A bracket kind of R inverse T, SU, modulo T minus A prime U minus 1, so I'll suppress all the subscripts. This map to U inside M of A, this is a homeomorphism. Onto here, in particular, this guy is compact, so closed. Okay? So these Laurent domains, and more generally also the rational domains, these are all going to be compact subsets. They will be closed, but they do have this very nice mapping property that gives us a way to think about them. Okay, so that said, let me just make another remark that by using massive extension of the base field, the acyclicity results of Tate and Kiel do carry over to create a theory of, well, tentatively I'll just call it coherent sheaves in quotes. And the reason I'm putting coherent sheaves in quotes is because we're going to want to take, in this aphanoid setting, we haven't discussed globalization yet, we want to take a finite module over these aphanoids, and they do in fact have natural Banach structure, so there are no funny surprises there. But when we want to talk about coherent sheaves, at the outset, these are going to be things that we initially evaluate on Laurent domains or rational domains. So evaluate on closed sets. And so if you learn sheaf theory from Leray or something like that, sheaves evaluate on closed sets is of course the most natural thing in the world. But otherwise, it's a very surprising thing to do. And so suffice to say, these spaces, we will have a nice sheaf theory on the actual spaces, but the coherent sheaf theory is going to be not exactly part of the framework of ordinary sheaf theory, precisely because they're not going to be quite, well, they can be evaluated on open sets later, but at the outset, we also want to evaluate them on certain interesting classes of closed subsets. So in fact, to get the coherent sheaf theory off the ground does require a little bit of preparation, and so we're not going to sort of get into the technical details of that now. Okay, so that said, let me just again put in the warning that for globalization of these spaces, so of course, once you have this, in particular, there is a concept of structure sheaf, in quotes, so that does endow these topological spaces with some kind of an analytic structure, but in order to globalize, one really needs to identify a richer structure a richer concept than locally ringed space. Yes? Right, so finite modules have a natural Banach structure, and maps between them are automatically bounded, so there are no unexpected complications in that respect. Rather, you choose a presentation, and it's always a Banach structure on the quotient. The kernel is closed. All right, so the globalization, which will be discussed in my last lecture, you just have to keep in mind that the complication is we have to find a way to define a class of sort of structured spaces which, well, there will be ring spaces in the background, but we have to sort of keep track of the data of certain kinds of compact subsets over which we can evaluate things like the structure sheaf and define some kind of a gluing process. Okay? So life is going to be a little bit more complicated, but there are, of course, benefits to be paid off later. And actually, while we're on that topic, let me tell you, before I get to the last topic, which is a little bit technical, let me pose a question that you can think about. Well, I'm sure you have many other things to think about, but you can contemplate this if you have some free time. And in the last lecture, I'll explain to you how there's a question in classical rigid geometry, which, well, let me just tell you the question. So A is a classical strict k-aphenoid algebra. And suppose I is some ideal. And choose your favorite epsilons. Well, you don't choose the epsilons yet. And let Z be the rigid space cut out by the ideal inside the rigid space of A, and let U containing Z be an admissible open. And the question is, so here's the space X, space of A, here's Z, and here's your open U. And the question is, do there exist epsilon 1, epsilon n in the divisible group of the value group such that U, not only does it contain Z, it contains subtube around Z. Is a cofinal system of admissible opens around a Zariski closed set given by just defining small inequalities on a generating set of functions in the ideal? If these were compact spaces, this would be a very easy topology exercise, but they're not. So it's not obvious, and you can prove this by rigid geometry, but when I did it this way, the proof is way more complicated than you would expect. So I'll just say that by using Berkovich spaces, which are compact Hausdorff, you can give a very intuitive proof of this fact. So I'll just say the answer is yes, but this is quite hard in the sense that it's certainly much more complicated than you would have expected via just thinking in terms of rigid geometry. Mark Kissin also gave a simple proof of this by using Raynaud's formal models, but I think that the proof by Berkovich spaces is basically as short, if not shorter, but I think it's also a little bit more in line with your intuition for one to think about these as compact spaces. So we'll come back. I'll show you the proof of this using Berkovich spaces in the last lecture, but I want to end by talking about a topological structure on these aphenoid spaces that one does not perceive in the classical theory, but is in fact quite a fundamental notion in Berkovich's theory, which is the concept of the relative interior and boundary. And this does not correspond to the fact that you want to think about the closed unit disk as perhaps having that circle of radius 1 on the outside as a boundary. That's, of course, completely meaningless because you can always recenter the disk at any of the classical points. So it's not that that kind of boundary circle is going to be a boundary in this topological space in any way, but there is, in fact, a kind of a boundary which does sort of fit with your intuition that there should be something quite on the outside, like the Gauss point. So what do I mean by relative interior and boundary? So let's say I give you A to A prime is a map of k aphenoids. And a perfectly interesting example to keep in mind is just the structure map from K. All right? And now I want to define what I'm going to call the relative interior for M of A prime over M of A, although I really should just call it A prime over A. Because it doesn't just depend on the topological spaces, it depends on this ring map. So these are certain points in M of A prime. So let me say what they are, and I'll use a word and define what I mean. So I'll call this map phi. And the condition is that this map from excuse me, from A prime to the point, the residue field of the point, this is what's called inner with respect to A. And so what I mean by that geometrically, this sits over this. So I'll write it sort of pictorially. I want to put M of A prime inside of M of A cross a closed polydisk, such that this point goes into M of A cross, let me say, the interior. That's how you should think about it. So rigorously, what I mean is that there exists an expression for A prime as a kind of Banach algebra quotient of a relative Tate algebra over A with possible real radii, such that this point pulled back to this product space, when you project to the polydisk factor, it lands inside of a proper closed subdisk. So you can sort of present this over A in a way that this point is kind of away from the boundary. Okay? We'll call those points the relative interior points. And we'll call the relative boundary. So this is actually an open set. And the relative boundary is just going to be the complement of the relative interior. Okay? So, so as an example of this, in the case, well, let me just tell you some properties. Let me just end by telling you some properties of this relative interior and boundary, just to convince you that these are actually worthwhile notions. So some properties. Sorry, thank you. Okay, so first of all, if M of A inside M of A prime is an affinoid subdomain, so like a Weierstrass domain and so forth, the affinoid subdomains are defined exactly as in the classical case by a universal mapping property. The rational Laurent and Weierstrass domains are examples. You can think of those. Then the relative interior is the topological interior. It's just the topological interior in M of A of this subset, M of A prime of the subset M of A. So at least for affinoid subdomains, the relative interior is actually quite a reasonable notion. And also, if I give you a map of affinoid algebras, this is a finite map in a sense that respects the Banach topologies precisely when the relative boundary is empty. So in some sense, finite maps have no relative boundary. So that's, in some sense, that's actually quite a satisfying fact. And the last thing I want to mention is the maximum modulus principle. Well, you know, if I give you an element in an affinoid algebra, and now you look at the function, x goes to absolute f of x, the topology is rigged. This is, in fact, continuous on M of A. Well, so no big surprise, it attains a maximal value. That's not very interesting in this setting because this is a compact Hausdorff space. Nonetheless, there is a maximum modulus principle with substance, and the maximum modulus principle says that, in fact, the supremum of f of x over all x, well, it's a much more precise statement, but I'll just say something succinct for now. This is attained on the relative boundary. Whoops, okay, so there's a little complication because the relative boundary might be empty. So usually, anyway, there's an interesting subset of this space called the Shilov boundary. And maybe I should say this is for A over K. So there's something called the Shilov boundary, and this is always attained on that interesting subset. Okay? So the maximum modulus principle does still have substance in this context, but it's not just the existence and the attainment of a maximum. It's that it's located in some sense on a boundary. Okay? So those are the basic ingredients in the affinoid theory. And let me just again remind you that the complication in the globalization is precisely the fact that we're going to try to glue these spaces to each other along affinoid subdomains. These are not open sets. And so we have to somehow get beyond the framework of ringed spaces. And so that's what we'll do in the last talk. Thanks. Yeah, Joe. No. Okay. So and for the unit ball, yeah, I'm sorry. So the question is the relative boundary of the closed unit ball what you would think of as the naive boundary cut out by the condition absolute value of t equals 1? This is not true because you can always recenter the disk at any classical point. So intrinsically, there's no way to distinguish those from the other points. So in this case, the relative boundary is in fact just the Gauss point. All right? So it's actually just one point. And of course, in that case, the maximum modulus principle is a tautology. At the Gauss point, the absolute value is the yeah? So you see, in that case, not so interesting. But the relative boundary for the disk is in fact just the Gauss point.
So we still think of it like a generic point?
Yes. So this Gauss norm, in some sense, serves sort of like a generic point, but not literally, because the underlying space is compact Hausdorff. So in a topological sense, it's not the generic point, although there is a reduction map from this space onto spec of the affine line over the residue field, and the Gauss point is the unique point over the generic point of the affine line over the residue field. And when you pull it out, the whole space breaks up into a disconnected union of the pre-images over the closed points. So the Gauss point kind of holds the thing. It's like the force. It binds everything together.